All right, so problem of the day number 3 was a little bit tricky. It was an abstract problem because we haven't talked about phenyl groups and whether or not phenyl groups are electron donating or withdrawing, or whether or not they're ortho or meta activators or directors. So we have to do some reasoning here. And so before we even begin, do you think that a nucleophilic attack will occur at this position? That ortho position to the other benzene? I heard a no. Why not? Because of sterics. It's pretty crowded, so we can immediately say this one, let me actually write it down here, is blocked due to sterics. So even if it were an ortho para director, that ortho position wouldn't be favored. But then we have to ask ourselves, what would be favored, the para position or the meta position? All right, so now let's go through and try to draw both potential routes and try to make sense of what's going on here. So I'll label this route 1. And what we'll do is draw our fused rings and have it attack in the meta position. And I'm not going to draw out the full mechanism. I'll do that at the very end. I'll just draw a generic electrophile E+. So if it's a meta attack, this will come in, grab our electrophile, and we'll form our rhenium ion. And the positive charge will be right here. One thing I would do is try to draw the resonance structures for these guys. If you're in doubt, that way we can compare the stability of our intermediates. So let's draw some resonance structures here. Whoop. There should not be a double bond. There we go. And we can say, all right, let's move this one down. Draw the resonance structure. That would move the positive charge over here. We now have a double bond here, here, and so on. Oops. And then we can also have another resonance structure where this double bond can jump over. Can we have electrons come from the adjacent phenyl ring? Not without violating the octet rule. So in this case, we're kind of stuck. We can delocalize it in one ring at least. And this would move the positive charge over to this position. Whoops. Let me keep track of my double bonds in the right spot. There we go, here and here. All right, so this rhenium ion, we can delocalize it around that lower phenyl ring. So we can delocalize the positive charge across 3 carbons. But let's compare this to route 2, where we have a para attack. And again, I'm just going to use our generic electrophile E+. We'll have attack from the para position. And we get our electrophile here, have a positive charge. I guess I'll draw it on this side, keep it consistent. We can draw resonance structures. So let's draw out a couple of them. I'm not going to draw them all because I don't want to take up the whole space of the paper. So we can keep on delocalizing through that lower ring, but what's unique with this resonance structure? It's a tertiary carbocation, and what else is special about it? It can delocalize into the other ring. Technically, it's a benzylic carbocation, right? So we can actually show delocalization coming down from this ring And we can show quite a few different resonance structures. I'm just going to only draw this one for time's sake. But the key difference is that for route 2 versus route 1, route 2 we can delocalize across multiple rings. So route 2 is going to be much, much more favorable because we have the more stable intermediate. All right, now let's quickly go through and do the mechanism. Sorry, I know sometimes I don't give enough space. The first part of the mechanism is we take our nitric acid, we react this with our sulfuric acid, which I'll label H+. And I'm going to actually, let's do stepwise. I don't want to break my own rules. Then we can kick off water, form our nitronium ion. Oh. And the benzene ring, I'm just going to label this pH. We said it is going to attack in the para position. Kick up electrons. Looks like a D. pH. Have a positive charge here. We have a hydrogen. We've got NO2. Then, last but not least, what do we need to do? Restore aromaticity. So we show the last arrow pushing where we grab this proton, clamp down, and we get our final product. And let me actually draw out the full final product. All right, so the question is, what could we do if we wanted to install that nitro group over onto this position? Oh no. Does anybody have an idea for what we could do in order to get it installed in one of these green positions? Yeah, block it, right? So if we didn't want to get the nitro group onto that para position, but rather onto the ortho position, we could do reversible sulfonation. That would first install in the para position, block it, and then we can do the ortho attack by cranking up the heat, and then remove our sulfonate group using dilute sulfuric acid. So that's another trick we could use. But in this case, we're not using any blocking groups, and we're going to install the nitro group in the para position. So that was a little abstract. I just wanted you guys to get thinking a little bit critically, because if you actually do look up online whether or not a phenyl group's electron donating or withdrawing, it's not clear. It depends on a lot of different factors. So if you're ever in doubt, just draw out the options and try to rationalize which one has the most stable intermediate, because that means it has the lowest activation energy for the reaction. Are there any questions about this? All right, let's continue on. Yesterday we finished up talking about using blocking groups, which I kind of brought back again. This is very useful for trying to install something in ortho orientation to activating group in particular. But let's talk today about some more synthesis strategies we can use, and then we'll continue on and talk about some new reactions. All right, in your book, there's this really nice chart that kind of outlines all the reactions that we've covered in this chapter. The halogenation, both with bromine and chlorine, the nitration, sulfonation, Friedel-Crafts alkylation and acylation. And then we can continue on with some of these. So for example, if we have a nitro group, we can reduce it to an aniline. If we have a benzylic position, we can brominate it, which we covered in chapter 18 using radical bromination. Or we can oxidize benzylic positions to carboxylic acids. And then the recent one we learned is the Clemmensen reduction, where we've got the zinc and mercury. So on Monday, what we're going to do is we're going to have group problem solving. So I'm going to give you some synthesis problems, and you're going to have time to try to figure them out. But this is a nice flowchart to have ready. So if you do want to copy this down or print it out, you're more than welcome to as a study guide. The other thing that's really kind of useful for this chapter is, let's take converting a nitro group to an aniline. A nitro group is going to be a meta director, but as soon as we reduce it to an aniline, we've changed the directing capability, right? So in this case, an aniline is going to be an orthopara director. So if you do need to change your directing capability, you can do some of these simple reactions. Same thing with a methyl group going to a carboxylic acid. We know a methyl group is going to be an orthopara director, but carboxylic acid is going to be a meta director. Same thing with Clemmensen reduction. You can change it from a meta director to an orthopara director. And same thing with a methyl group going to trihalogenated species, in this case, the tribromide. So these are all really useful, but there's a couple important caveats I really wanted to emphasize. So two important caveats. And I kind of brushed on these earlier, but I wanted to emphasize them again. The first one is if we have aniline, is aniline going to be a an orthopara director or a meta director? Orthopara, right? Let's say I want to do nitration on this and install the nitro group into the para position. This looks fine on paper. What reagents would we need? Nitric and sulfuric. So HNO3 and H2SO4. The problem with this reaction is it doesn't work. It gets oxidized into a mess. Anilines are notoriously finicky. They tend to degrade. Even if you keep them in a bottle and they're around air for a long enough period of time, they'll degrade. If you're throwing in nitric acid, which is a very strong oxidant, it will just cause them to degrade before the nitration even occurs. So nitration doesn't work on anilines. Doesn't. Oh, shoot. I keep on hitting buttons.
Is there another way to do it without nitration? Is there a regular reaction?
Not really. In this case, there are more advanced synthetic techniques, but this is one big limitation from this chapter. We're not going to get into those advanced techniques. The second important caveat is that Friedel-Crafts reactions can't be done on rings that are deactivated. So let's write this down. And this applies to both. Oh. Doesn't work on moderately or strongly deactivated rings. And this simply is due to the rings not having enough electron density on them to perform the nucleophilic attack. So an example of this would be if we had a nitro group. Is a nitro group an orthopara or meta director? It's meta. So if we try to do the Friedel-Crafts acylation, we would initially say, well, we should install this group in the meta position. But the problem is this reaction does not occur simply because this is 2 electron withdrawing. Yep. Oh, shoot. Thank you. That was my goof. Good catch. This is 2 electron withdrawing. I'm glad I have you guys here. All right. The other thing that's important to remember with synthesis is that it's very important to remember the order in which you add your substituents. Because we know that some groups are directing into the ortho-para position, others are directing into the meta position, so sometimes you need to pay particular attention to the order or sequence of reactions. And let's actually go through one of these because sometimes these synthesis problems get a little bit overwhelming. And especially with these, when you've got multiple substituents coming off a benzene ring, trying to work backwards can be a little bit more challenging. So let's do a practice problem here. All right, so let's say we have benzene. We're going to do a multiple step reaction, so I'm just going to show forward arrows. We don't know how we're getting there. Oh, this is a good naming question. What would this compound be named? What's the parent? It'd be acetophenone would be the parent, right? Because we've got that acetophenone functionality on there. We've got the bromine in the 4 position, so we could say 4-bromo, 3-nitro acetophenone. So again, this is one where we need to identify the correct parent on here. All right, so now let's try to figure out the correct route through which we can make 4-bromo, 3-nitro acetophenone. And again, just like with most synthesis, we want to work backwards. So let's compare our options. Let's say we're going to install our bromine last. That would mean our starting material would have to have the nitro group on and our ketone on. And we could go to our product. Or we could install the nitro group last and have our bromine on. And we could get to our product. Or, last but not least, we could leave our nitro group on and our bromine on, and we could install the ketone on last through a Friedel-Crafts acylation. So let's quickly write down the reagents. What would we need for that first reaction if we wanted a bromine on? Or FeBr3. That's the most common one. What about the next one when we're installing the nitro group? Yep, nitric acid and sulfuric. And then for the last one, we would need an acid chloride and aluminum trichloride. So the question is, which of these 3 would be the best? We have to pay attention to directing groups, right? So let's take a look at this nitro group. Is it going to favor ortho, para, or meta? It's going to favor meta, which the only meta position available is right there. What about this guy? Where will it favor? Meta. It's also electron withdrawing, and the only meta group is available there. Do we want our bromine installed in that position? No. We want it installed right here. So in this case, that reaction's kind of out of the question. We're not going to get the correct regiochemistry for that. All right, now let's do the next one. We've got this bromine here. Is that a ortho-para or meta director? orthopara. So it's the weird exception where even though it's electron withdrawing, it's going to be an orthopara director. So it could attack either here or here. And then we can take a look at the ketone. We just said that that's going to be a meta director, which means that it could attack here or here. So if we're looking at this, does it matter whether or not we're attacking that top carbon or the bottom carbon? No, it's symmetric. In which case, this reaction, would that work? Yeah. So just for the sake of being thorough, let's double check our last one and see if maybe there's something better about it. All right, so now we've got this nitro group that we said is a meta director. So that can favor here or here. And then we've got a bromine that could be ortho or para. Would this be better or worse? Worse. We might get a mixture, right? So the main problem with this, we might get acylation here.
Since you're really deactivated, you can't do Friedel craft either, right?
Exactly. That's the other really big pitfall with this reaction. You might get acylation there, hypothetically, if it were to work. The other main problem is it's deactivated. So in this case, I'll abbreviate Friedel-Crafts as FC won't work. So we've got two major problems with this reaction, which immediately takes us to the option 2 as being our best option. All right. So we'll label this part 1, and now we'll work backwards. If we need to go from here backwards, so I'll do step 2, working backwards. So that was our ketone para to our bromine. So we could start with our bromine on first. Do our acylation, or we could just start with acetophenone and do our bromination in order to get to our intermediate. All right, let's do the same thing we did before. If we've got bromine, it'll favor orthopara. If we've got the carbonyl group, which will that favor? Will favor meta, right? We definitely don't want meta substitution, which means that reaction 2, which would have required Br2 and Fe Br3, is out of the question. So this won't work. But the top one will, right? Bromine's relatively small. Bromine's relatively bulky. So in this case, the ortho positions will be disfavored because bromine's a giant atom, right? So in this case, they're blocked.
If you blocked, how come that wouldn't work on the previous one? You said you might get that mixture, but it's blocked.
So yeah, that's another thing too, is we could also invoke sterics. So option 3 on the top one has a lot of things going against it. That would, I'd say, be the worst option.
No, I'm saying it would install there, it would result in the pair position, so that would be where you would want it anyway.
Yeah, so you might get a small mixture, you're correct. But the biggest thing is it's deactivated, and Friedel-Crafts won't work on a deactivated ring. Yeah, that's a good point. All right, so for this one, what reagents would we need? We need aluminum trichloride, but what's the other reagent? The acid chloride, right? All right. So now if we go through, we can plan our synthesis. We know we're going to start with benzene. We need to make bromobenzene first. So we can do Br2 and iron tribromide. Install a bromine on there. I'm not going to show the mechanism. Then we can do Friedel-Crafts alkylation. Actually, I'm going to flip the ring, but you'll get the same idea. They're going to be paired to one another. And then last but not least, we'll do our nitration. Oop. So the plan of attack is similar to other synthetic problems where we work backwards, but this time we have to pay a lot more attention to the directing groups and whether or not they're ortho-para-directors or meta-directors. Does that make sense? All right, if we have time at the end, we might go back and do another practice problem, but I wanted to continue on to the last couple reactions in this chapter so you guys can do your sapling problems. All right, all the reactions we've seen so far involve benzene being the nucleophile, but benzene's really weird. Benzene can be an electrophile too. So let's take a look at some of these reactions that have benzene acting as a electrophile. So the key thing is you have to have a leaving group, which I'll arbitrarily show as bromine. And you have to have a very strongly electron withdrawing group. So I'll call this our leaving group. And then, I'll call this our electron withdrawing group. This is key for these reactions to work. If you do this, you can have sodium hydroxide in step 1. And then you can have an acidic workup in step 2. And you can swap out the bromine for an alcohol and form a new phenol. So this is pretty weird because we know that hydroxide is not an electrophile, it's a nucleophile. So we have to figure out what's going on. And the mechanism is pretty straightforward. First step is a nucleophilic attack, but this time coming from the hydroxide, not the benzene ring. So the hydroxide will come, tack in, kick up electrons onto that position, which is ortho to the bromine. Actually, let me draw out all our bonds for this step. This looks pretty unstable, right? Looks a lot like a Grignard reagent. We have a carbon with a negative charge. But what else could maybe stabilize that negative charge? Resonance, right?
Where's your hydroxide?
Nope. Shoot, thank you. Yeah. Got bromine and hydroxide. Sorry about that. But let's draw the resonance structure we can get. So I'm going to draw the resonance structure using a blue arrow. Now we've got a double bond to a nitrogen. Each oxygen has a single bond. So now we avoid carbons with negative charges. Now the negative charge is on the oxygen. Oxygen's a lot more electronegative. So in fact, this is the major contributor. This is the minor contributor. And what we call this, let me change colors, is the Mizen complex, which is a mouthful. Let me make sure I spell this right. Heimer complex. So Misenheimer complex. And this is stabilizing that negative charge simply because we've got a very, very strongly electron withdrawing group. All right. Now we'll show our last step. And I'll go back to our red arrows. In this last step, this oxygen dumps down. Kick electrons back here. Kick electrons here. And we eject off bromine as our leaving group. And we restore aromaticity to the ring. So we've got Br minus as a leaving group. Question is, what's that? Are you saying why don't I have the double bond on this side?
It can rotate, so it's okay.
Yeah, the sigma bond can rotate between the carbon and nitrogen, so that's fine. So the question is, if we go back to the overall reaction, what's the deal with the hydronium in that last step? So you see step 2 on my example? I say we need to...
Oh, it's propane.
Yeah, so the other interesting problem with this reaction is you really have to push it because we're breaking aromaticity. So if we've got more hydroxide around, let me keep my color scheme the same.
Oh, the depronate.
The extra hydroxide would deprotonate it to form our phenoxide, which is not exactly desirable. So in a second step, we just reprotonate it. I know it's a little steppy, but it's important to remember the order of procedures is that you have to do this in a 2-step process in order to get to your final phenol.
Somebody asked a question.
What's that?
Oh, we were saying that the double bond should be on the other atom, not in the structure on the far right.
Oh, so with my arrow pushing up here, I drew this electron going down to this bond.
Yeah.
So,
But you have a charge.
The negative charge of the bond.
Your negative charge to the other one, or you should switch it.
On the bottom right.
oh, yeah, thank you. Yeah. All right, you're correct. Because I moved that double bond, the negative charge should be over on that other oxygen. You guys can ask TCC for a refund later, I guess. All right, and then we can get to our final product. All right, let's go back and take a look at this.
Can you go back? Sorry. Okay.
So the Mizenheimer complex is the whole reason that this thing works. What happens if we've got a nitro group?
What is the point of that? So it's just keep continuously going back and forth between.
No, so you see how I've got step 1 with hydroxide? If you have excess hydroxide, it will continue and deprotonate your phenol. And so you have to reprotonate that in the second step. I know it seems kind of silly. Oh, well, in this reaction, you have to usually use forcing conditions and high temperature, so you're going to deprotonate it. Yeah. We have to make sure to reprotonate it. But let's take a look at the mechanism here. What happens if that nitro group's in the meta position to the bromine? Will it work? It would not work because then you can push that negative charge onto the nitro group. So for nucleophilic aromatic substitution, we have very specific criteria in order for it to work. So 3 main criteria to consider. The first one is you must have a strong deactivator. Typically what you see is a nitro group because those are very, very strongly electron withdrawing. If you don't have a strong deactivator, you're not going to be able to stabilize the negative charge on the ring. The second thing we said is that the deactivator must be ortho or para. If it's meta, it won't be in the correct position to pull that negative charge out of the ring. It won't stabilize your Mizen complex. The last thing is that you must have a leaving group. If you don't have a leaving group, you're not going to get this reaction to work. You're not going to get a methyl group to fall off. You're not going to get an alkyl group to fall off. Typically what you need is either halides or a tosylate. So if you remember, we can turn an alcohol into a good leaving group by tosylating it. You can use that sometimes for these reactions as well. So it's a pretty simple thing. The key to look for is instead of your benzene ring being the nucleophile, you're substituting in a nucleophile and popping off a leaving group. All right, the very last reaction for this chapter, I promise.
All right. Then get to the exceptions.
Is Elimination Edition. And this goes back to a question we had on our final exam that bugged a lot of people about benzine. This is where it all kind of comes together. And this started out with some weird observations. They said, all right, let's take bromobenzene. And what we'll do is first react this with sodium hydroxide. And second, we'll react this with sulfuric acid. So they were trying to do nucleophilic aromatic substitution. So this is just like what we saw on the last page. We've got a leaving group, but we don't have a nitro group.
Are you using sulfuric acid or?
Nope. We're trying to do a substitution here. Did I say sulfuric acid? Oh, sorry. Just acid. So in the first step, they said, all right, let's just try to do a nucleophilic aromatic substitution, but without a nitro group. What they found was they got no reaction. Right? Not very interesting. It goes along with the previous rules that I was saying. You have to have a nitro group in the ortho or para position in order to get nucleophilic aromatic substitution. But then, just as all chemists do, when something doesn't work, no, chemists don't give up. When something doesn't work in chemistry, the first line of attack, you heat it up hotter. You're like, I'm going to make it work whether it wants to go or not. I'm just going to keep on heating it until it either turns into a black tar or the reaction works. And surprisingly, the reaction works. You have to heat this to over 300 degrees Celsius, so it doesn't work on any complicated systems. Most of the time you would make a black tar out of this, but on really simple systems it does work. And the question was, what the heck is going on that can make this work? So let's take a look at the mechanism here. So we've still got our good leaving group. We've got hydroxide. But this time, instead of the hydroxide immediately attacking that position that the bromine's on, it'll actually just act as a base. And so this hydroxide will come, grab an adjacent proton, clamp down, and eject off our bromine. Let me actually draw this more clearly. You guys can keep yours the same. I just don't like my drawing. There we go. This is benzine. And this was the question I had on the final exam on whether or not benzine's aromatic or anti-aromatic or non-aromatic. And a lot of people said that they thought it was anti-aromatic because if you count the electrons in there, you've got 8. But what's kind of the hitch here? You can only have one pi bond in a p orbital, right? Or at least in an orthogonal p orbital to the rest of the ring. So in this case, the delocalized ring system does have 6 electrons in it, so benzine is technically aromatic. Does it look like a very happy molecule? No. sp3 bonds, or sorry, sp bonds want to be 180 degrees. This is very, very far out of linearity. It's not a stable compound. It's very high energy. So in this case, what happens is you can actually have an additional attack where the hydroxide will add in very, very quickly to benzine and dump electrons back onto the adjacent position. And then all you need is some sort of weak acid around. Usually it's actually another phenol molecule because the hydrogen on that alcohol is fairly acidic. Oh, sorry, I'm missing a double bond there. There we go. And then you can have this double bond come grab its proton back, form your conjugate base. And you're good to go.
So what is it about heat that makes that?
That has to do with the benzine. If we look at benzine, I said it's a very, very unhappy looking molecule. There was actually a lot of debate. People said benzine doesn't exist. There's no way it could possibly exist. You guys are all off your rocker. It's just too high energy. You can't strain an sp bond that way. And benzine, to kind of go off on a tangent, can be represented a couple different ways. There are actually a lot of experiments that say that benzine actually isn't a true triple bond. It's more of a diradical. It has more diradical character than triple bond character. No, it's just done with super high heat. The other interesting thing was you can actually intercept benzine. And the way they intercepted benzine was doing this sort of reaction. What's this called? Diels-Alder. So to prove that they made benzine and that they weren't doing nucleophilic aromatic substitution, they would sorry, I've got my double bonds in the wrong spot. Double bonds here. You can do a Diels-Alder reaction. Oh man. Sorry, I'm all over the place today.
You showed me giving extra attention to those 110 students. I'm sorry, I'm gonna redraw this slightly differently. I don't like the way I drew this. My oxygen was pointing in the wrong direction and was gonna make this look ugly. There we go.
Okay.
Okay. Start over.
There we go. Now this won't look as ugly. So when you do this Diels-Alder reaction, you can restore aromaticity to the ring, and you can actually trap your benzine intermediate. And this is some of the strongest evidence that benzine intermediates are actually responsible for this reaction.
So we've got this oxygen kind of sticking out of the board towards us there. So you can trap Benzine intermediates, and that's the strongest evidence that these occur. The other reaction that's more common than reacting it with hydroxide is using an even stronger base. Hydroxide requires really, really high temperatures. So usually it's done with sodium amide. Because it requires lower temps. Instead of heating this thing up to 350 degrees, you can do it at a more reasonable 150 or something like that. Nope. So in this case, let's take a look at what would happen if we had our leaving group.
Can you throw up, please?
Yeah. Let's say this time we've got sodium amide, with sodium having the positive charge, the amide having the negative charge, and ammonia. This is a stronger base than hydroxide, right? If we look at our pKa table, this is a much, much stronger base. So the first step will be the amide coming, clamping down, kick off our bromine. Then if you've got more sodium amide around, this can attack in, kick electrons over. Now we've got all this ammonia around too. So ammonia can act as a weak acid in this reaction. And we can regenerate our sodium amide. And we can make anilines this way. So really, addition and elimination is only used for very, very simple systems. If you have an electron withdrawing group, the nucleophilic aromatic substitution mechanism will predominate. If you don't have a strongly electron withdrawing group, addition elimination predominates. But you have to have super high temperatures or a very, very strong base in order for this reaction to work. No? All right, so I think we're going to leave off there. Try really hard to get through the chapter on sapling, and then when we come in on Monday, we're going to do a lot of synthesis problems as a group and try to present them on the board. Just a second.